Hi, in this problem we have two vertical forces, which is these two 4 kilonewton vertical forces applied to a beam of the cross section shown, which is this one right here. So this is a composite shape cross section. The half part is square and the top part is half a circle or a semicircle. We are asked to determine the maximum tensile and compressive stresses in the portion BC of the beam. Portion BC. The reason why they ask us to find the maximum tensile and compressive stresses in portion BC, because when you do the shear moment diagram for this beam and these applied loads, you will figure out that the portion BC we will have pure bending, and we will discuss this further. Now in this beam where we have two vertical forces, 4 kilonewton, and these two vertical forces are transverse loads. The transverse loads mean you have loads that act perpendicular to the central axis, which is the yellow dashed line. We call it the central axis or the longitudinal axis because it runs along the length of the beam, where you have loads that's being applied at an angle of 90 degrees. These types of loads are called transverse loads. These transverse load will cause or will produce an internal shear stresses in the beam. So this is a different cross-section beam, and this is the shear stresses. These shear stresses will generate a net shear force, and that's what we want to figure out in if you are asked to find the shear and moment diagram. And the external moments, like the moment caused at the fixed axis right here at C, it will cause internal normal stresses. As you can see in this cross section, at the top we have compressive forces. In the bottom we have tensile forces. They are opposite and equal, opposite in direction, equal in magnitude. Therefore, they cancel each other and they generate an internal net moment, as shown in here. So what we want to do is we want to, the goal in here is we want to determine, one, where is the pure bending happening in portion AB or BC. Two, we want to find the maximum bending moment that happened, and to do so, we need to draw the shear and moment diagram. So the first step, we will draw the free body diagram, and we will represent our beam with this yellow dashed line, which is in the previous slide. We said this is the central axis or longitudinal axis. At this beam, it starts all the way on the left-hand side with 0 meter at A location, and we have a vertical force of 4 kilonewton. Going to the right, 0.3 meter at location B, we will have an applied load of 4 kilonewton or concentrated load. Going 0.3 meter again, which will give you 0.6 meter away from the 0 meter location at A. At C, we have a fixed axis, a fixed support. Fixed support restricts the movement in the vertical and horizontal direction. Also, it restricts the rotation, or in other words, the moment. The only vertical force applied, horizontal force, is C sub x. So that's why C sub x will be 0, so we can remove it. Next, we will sum the forces in the y direction and equal it to 0, and the forces going up will be positive. So this one 4, this one negative 4, and this one positive cy. And we will equal all this to 0. So that will give us that the vertical force is 0. So this one can be removed. Next, we will take the sum of the moment at C, where going counterclockwise is positive, clockwise is negative. And remember that a moment is force times the perpendicular distance to the axis of rotation, and in this case is at C, where we are taking the moment. So if we go all the way to the left, the 4 kilonewton times the perpendicular distance, which is a distance of 0.6, will cause the beam to rotate clockwise, which will be negative. And since we flip the force, this one times 0.3 meter away will give you positive. So that's what we're gonna have in here. And now we can solve for the moment at C, which will equal to 1.2 kilonewton times meter. So we can erase this and it will give us 1200 Newton times meter. And since it is positive, that means that our initial assumption that the moment is going counterclockwise is correct. The next step toward finding the shear moment diagram, what we want to do is we want to deal with each section by itself. So here we have section AB, and here we start from the 0 meter going all the way to B at 0.3, and along the length of portion or section AB we want to make a cut. So here on the right, that's what we did. We start from the 0 meter at the A location and we move an arbitrary length x, and then we make a cut. And our goal is to find an expression that describes the internal net shear force as a function of x, and the internal net moment as a function of x. So what we will do is we will sum of the forces in the y direction equal to 0, where up is positive. So here we will have a 4 kilonewton positive and a negative shear going down equal to 0. We solve for the shear force, and that will give you a 4. So it will give you a constant value, 4. Next, we will take the sum of the moment at x and equal it to 0. And remember, force times the perpendicular distance, which is x, and that will cause the beam to go clockwise. So that's why we have negative 4x plus m, the moment at x. So the internal net moment as a function of x will equal to 4x. So this is a function of a line. And remember, this internal shear force between A and B is valid between 0 and 0.3. And this one is valid between also 0 and 0.3. Next, we will make a cut in the other portion, which is B and C. So that's what we're gonna do on the right side in here. We start from the 0 meter, go all the way to B, then we're gonna take an arbitrary length from B and an arbitrary length from B and X, and then we will make a cut, and our goal is to find the internal net shear force as a function of X and the internal net moment as a function of X, where this X is between 0.3 and 0.6. So here we will take the sum of the forces in the y direction equal it to 0. And here we have 4 positive, this 4 negative, and this V is negative. So 4 minus 4 is 0, so that will give us that between B and C, or between 0.3 and 0.6, the shear force is 0. And that does tell us something. It tells us that because we have because our shear force is 0, it means that our moment between B and C will be constant. So we will take the sum of the moments at x equal to 0, and we will start all the way from the 0 meter, 4 kilonewton times x, and the 4 kilonewton will cause the beam to go clockwise, which will be negative, and 4 kilonewton times the perpendicular distance to the cut, which will be x minus 0.3, and that will make the beam go counterclockwise positive. And here we assume that this internal net moment is positive, and that's what we're gonna have in here. Next, it will be minus 4x. 4 times x will give you 4x, 4 times minus 0.3 is minus 1.2, and then we can solve for moment at x. Minus 4x plus 4x is 0. So it gives us that the internal net moment as a function of x will be 1.2. In other words, it will be a constant function, and that's right, because the shear force is 0, and this only valid between 0.3 and 0.6. So now we will draw the the shear and moment diagram. At A, we're going to have the 0 meter. At B, we'll have the 0.3. At C, we'll have the 0.6. So here on the side, we will write, okay, so what do we know between 0 and 0.3? The internal shear force function is 4, and the internal net moment is 4x. The x, when it is 0, it will give us a value of 0. When x is 0.3, it will give you 1.2. Now from 0.3 to 0.6, we'll start equal to 0, and the moment will be constant 1.2. So now let's draw the shear diagram. Here at A, we have an external load of 4 kilonewton, and from 0 all the way to 0.3, we found that the internal shear force is constant 4. Then at B, we have an external load applied on the beam at the value of 4 kilonewton, so we will drop down 4 kilonewton back to 0. And between 0.3 and 0.6, the internal shear force is 0, so that's what we have in here. Next, what we want to do is we want to find the the moment diagram. So we start from 0. So this one between 0 and 0.3, it is 4x, which is a function of line. So we will connect these 2 points right here, 0, 0, and 0.3 and 1.2. And then between 0.3 and 0.6, we have a constant moment, which is B and C. And then we have a positive that goes from 0 all the way to 1.2. So now we close the moment diagram. Because this is constant, between B and C, we have pure bending. So for us to find the maximum compressive and tensile strength, we will use the value moment to be 1,200 Newton times meter. So let's isolate portion BC, all right? And let's isolate it, and let's consider this cross section or any cross section. So we found that at portion BC we have a positive moment, which means that the beam will concave up. If you place your hand at these 2 arrows, you will see that the beam will concave up. So this, as we said, this is portion BC, and here we have the moments, applied moment, and this right here is the orange. We call it the longitudinal plane, a plane that run along the length of the beam, as you can see. And as you can see, this plane, we can also call it the bending moment plane, because that's where the moment happens. And now what we will do is we will place the origin point of a coordinate system at the center of the cross section. So finding the center of the cross section is something important to find the compressive forces and tensile forces, compressive stresses and tensile stresses caused by bending. So here we will have this, that is the x-axis, or in other words, the neutral axis. Then the vertical one will be your y-axis, and in the bottom will be the negative y-axis. This one will be your z-axis, and as you can see, it's parallel to the plane, to the bending moment diagram. And here you will have your rotation at the z-axis, and this is our origin. So this is our cross section right here. So now let's draw this horizontal line, which is z, and then our vertical y line, y. So this is our, now if we took this as a side view, when we apply these moments, that's what we're gonna have. This will be our neutral axis right here, and this will be our C value. The C value is this, and from the neutral axis or the x-axis all the way to the top of the beam, or all the way to the bottom of the beam. And here we are told that we have positive moment. So in here, between portion B and C, we found that we have positive moment. Positive moment means that the beam is concaving up. So that means top will be compression and top and bottom will be tension. And that's what we have right here. Here on the top, we have compression because the forces are pushing on the beam. And in the bottom, we have tensile because the forces are pulling on the beam. And this will cause an internal net moment. And remember, this is called the neutral axis. And it's important to remember that a neutral axis passes through the centroid of the cross section. So it's important to find the center of your cross section because that's where you're going to have your neutral axis. And the neutral axis plane will always be perpendicular to the bending moment plane. And the reason why we call it neutral, because as you can see from this demonstration, that at this point where the neutral axis passes through, the forces or the stresses is zero. So we are asked to find the maximum. So the question, where does the maximum happen? As you can see, the maximum happen all the way on the top or all the way on the bottom. So here at the top, we will have the maximum compressive stresses. Because why do we say compressive? Because we are told we are given positive moment, and positive moment concave up, the top will be compressive, the bottom will be tensile. So at the bottom in here, you will have maximum tensile stresses. All right, so in here, what we want to do is we want to find the maximum tensile now and compressive stresses. And we will use something called the elastic flexural formula. The reason why we call it elastic because the applied external load on the beam causes internal shear forces and internal normal stresses. These forces, these stresses that are generated, they will be within the yield stress. In other words, if you remove these external loads, the beam will go back to its original shape. There will be no permanent deformation. And this function is the normal stress, the maximum one, equal to minus moment times C divided by I. All right, so now let's take a moment and make sure that we know what these three terms mean. So this is moment. That's where the pure bending is happening. So we want to find the maximum bending that happened at portion BC, and we found it to be 1.2 kilonewton times meter. Next, we want to know what is C. C is the distance from the neutral axis or the x-axis all the way to the top of the beam, which will be your positive y-axis, or all the way on the bottom of the beam, which will be your negative y-axis. So, and then the I is the area moment of inertia with respect to the centroid of the cross section, of the entire cross section. Now you'll ask a question, what is this negative? All right, why do we have negative? Let's think about it together. Let's take a look at here on the top left-hand corner. Here we are told that we have positive moment. Great. What does that mean? It means that the beam will concave like this, concave up. All right. Because it concave up, the top of the beam will be compressive, and therefore the result from the normal stresses will be negative. When you have negative stresses, it means compressive stresses. On the bottom of the beam, we will have tensile, tension. That will be positive. So when we that means positive stresses indicate tension. All right. So why do we use again the negative? So let's think about it. We are told that we are given a positive moment, and that's what we have in here, a positive moment. At the top of the beam, where we're going to have, which will be the positive y-axis, it will be positive divided by positive. So positive times positive is positive. Positive divided by positive will be positive. Positive times negative will be negative. So that means this is compression. Now, what about tension? All right, again, so we have positive moment, and that's what we have in here. At the bottom of the beam, or in other words, where you're going to have the minus y value, which was right here, minus divided by positive. Positive times negative is negative. Negative divided by positive is negative. Negative times negative is positive. So that's why we put the minus value in here. So it can spell out the correct sign that can tell us whether we are dealing with compression or tension. So let's flip it, and let's say this is minus bending. We found when we did the Freebody diagram and we did the internal shear and internal net moment diagram, we found that we are dealing with a negative moment. It means that the beam is concaving down, just like this. So the top will be compression, the top will be tension, which will give us positive shear stresses, and the bottom will be compression, which will give us negative shear stresses. Negative in normal forces and normal stresses. The same thing like we did before. Here we have a negative moment. That's what we have in here. And at the bottom of the beam, it will be the minus y-axis. That's what we're going to have in here, divided by positive. So if you did this, the answer will be negative. So that gives us compression. Same thing for tension. Tension in here, negative moment. And at the top, the tension happened. The top is positive y-axis. That's what we have in here, divided by positive. So negative times positive is negative. Negative divided by positive is negative. Negative times negative will give you positive. So positive normal stresses is tension. That is why we have this negative value. Now what we want to do is we want to find the centroidal coordinate of the cross section. This is a very important point, and it's very true, and I highly advise you if you want to become good at this chapter 4, pure bending, and the remaining, it's a good thing to practice your how to find the centroidal coordinates of different shapes. Now there we have tables that tells us the centroidal coordinate expressions that we can use to find the centroidal coordinates in the x and the y direction. But sometimes we will be dealing with shapes like this one that we have that we don't have it in our tables. So what we will do in here is we will divide this cross section into two known shapes that we can refer them back to the tables that we can find in our reference books. So in here we are given that this is 0.05, and as you can see, this one can be divided to two sections of 0.025, and when we make a cut in here, we will have a symmetry in here. So this cut will be our y-axis, and here and in the bottom of the beam will be our x-axis. So right here, the first point we can start it from x, which will be equal to 0, and we want to find the y coordinate of the first shape and the y coordinate for the second shape. And remember, it's with respect to the x at the bottom of the beam. And pointing out the remainder dimensions of this cross section, the height of this beam, the height of this first shape is 0.025, and from this the radius will give you 0.025 meter. And we said that we will divide this between shape 1 and shape 2. So what we want to do is we will use this expression to find the vertical or y direction, or in other words, the vertical centroidal coordinate. So that this tells us the sum of the vertical centroidal coordinate of each shape times its area, divided by the sum of the areas that we're dealing with. So what we will do in here is we will create different columns. The first column is shape, then area, then the central coordinate in the for shape 1 and shape 2, and then we multiply the area times the center of each shape. So we have shape 1, shape 2, and then the sum. And remember, we need the sum of the area, which is this column, and the sum of the y times a, which is this one. So first thing, the area of shape 1 is a rectangle, which is 0.05 times 0.025, and that's what we have in here. So it will give us a value of 0.00125. Next is the area of shape 2. 2 is a half a circle. Area of a circle is pi r squared, then we divide it by 2. That will give us an area of a semicircle. Then we will find that the area for number 2 is 0.000917. We sum these two values and we will get this one. So now we were able to find the sum of the areas right here. Now we want to find the center of shape number 1 in the vertical direction. So that's easy. This one will be symmetrical, so that means we can cut it in halves. So half of 0.025 meter will be 0.0125. But for shape number 2, the vertical, this is a semicircle, so we can refer to our semicircle shape in here. And as you can see, we are interested in finding the vertical coordinate, which will be this one that runs through the center. So we will use this expression, but remember, we start from the bottom of the beam. So we will go up 0.025 plus this expression. So you start from the bottom, going all the way up here, where my pointer is at, plus the expression to find the center. And that's what we're going to have in here, which is 0.0356. Next, we will multiply the area by the centroid of the shape, and the area of shape 2 by its centroid. And these are the values that we're going to have, and we're going to sum these two values, and that's what we're going to have. So now we found the sum of a times y, which is this one right here. So now we will plug in the values that we found. So we found that our center of the whole cross section is 0.02266 meter. from the x-axis, so it will be somewhere here. So that will be our center, 0.022 from your x-axis. Now there's something important that you need to do after you find out your centroid, since we have these values 0.0125 and 0.0356, is when we want to find the area moment of inertia, we need to find the area moment of inertia with respect to the center of the beam. So we will need, in this case, to use the parallel axis theorem, which will require us to find the distance between the center of the beam, which is at C, and the center of each shape, like shape 1, which is 0.0125. So the question is, what is the distance between them? So here what we will do is we will subtract 0.022 minus 0.0125 meter. Next, we want to find the distance between the center of the whole cross section and the center of shape 2. So at center shape 2, we were told it's 0.035, so it will be what? 0.0356 minus 0.02266 meter. So the distance between them will be 0.01294 meter. All right, so now let's remove these axes. So now we will put our y-axis and our z-axis. So now we have our coordinates, and we place our the origin of our coordinate at the center of the beam, and through the screen or out of the screen, that's your x-axis, and the z is your axis of rotation. Another thing that we need, since we have this information in front of us, in the flexural formula we have the c value. We said that the c value is the distance from the center C, where the neutral axis or the x-axis is passing through, which run along the beam, all the way on the top where the maximum stress happen, and all the way on the bottom where the maximum stress happen. So to find all the way on the top, what we will do is the following. So we will go down from here all the way down here. This is 0.025 meter. That's what we have in here. Plus this distance between my cursor and the center, and that will be 0.025 minus 0.02266, and that's what we have in here. And when you do this, it will give you 0.02734 meter. Now what we want to do is we want to find all the way in the bottom. That's simple. That will be minus 0.02266. As you can see, minus, because it's in the minus y direction. So now we can remove this, we can remove this, and let's write down our flexural formula, and let's see what we got. We got we got here the C value, which is 0.02734 at the top, and minus 0.02266 at the bottom of the beam. All right. Again, let's write our formula. We found the C value. We found the M value from the internal shear and moment diagram, which give us as 1.2. So now what we want to find is we want to find the area moment of inertia. That is the final thing that we need to find the compressive and tensile stresses. So in here, what we will do, let's remind each other that the distance between C and the center of shape 1 is D1, and its value is 0.01016 meter. And the distance between C and 2, or in other words, that's where we are shifting our axis of rotation from 2 to C. That distance is D2, which is 0.01294 meter. So now let's take a look at shape 1. At shape 1, the first thing, the B correspond to 0.05 and H correspond to 0.025. And in here, the axis of rotation happens at the Z. And the Z-axis in here correspond to the X-axis in here, in the reference. So here, what are we looking for? We are looking for the area moment of inertia, an I value, okay, that passes through the center of the shape, which is the square C. So we will do, so it will be either these two, and with respect to the axis of rotation, so that will be the X. So we will use this expression right here. So now let's write down this expression. So the new area moment of inertia for shape 1 will be this expression, base times height cubed divided by 12, plus, now we will use the parallel axis theorem, the area of shape 1 times the distance. So what we are doing now is we want to shift the axis of rotation from the center of this, the center of shape 1 to the center of the whole shape. So that's why we need to find the distance between them. So now we will plug in the values. So we said that the base is 0.05, the height is 0.025 meter cube divided by 12, plus the area from the previous slide. We found that the area of the square is 0.0125 times the distance between the two axes is 0.01016 squared. So let's write here on the side our new area moment of inertia for shape 1 with respect to the center of the whole cross-section beam. It will give us 1.94 times 10 to the power minus 4 meter to the power 4. The next shape is shape number 2, which is this, which is a semicircle. The A is our radius, 0.025, check, and the x-axis correspond to the z-axis in here, all right? And so we can use the expression, the first expression in here. So the new area moment of inertia for shape 2 will be this expression that we have in here, plus the parallel axis theorem, which will be the shape of area 2 times the distance between the center of the shape and the center of the cross section and the center of shape 2. So what we will do is we will plug in these values as you see in here. Then we will find out that for the new area moment of inertia for shape 2 with respect to the center of the whole cross section is 2.07 times 10 to the power minus 7. Now we will add these two numbers to give us the area moment of inertia for the whole shape. You can convert this to millimeter by multiplying it by 1,000 to the power 4. And this is our area moment of inertia right here. So now we found the I value. All right, so now we have the M, we have the C, we have the I. It's only a matter of plugging in the values that we found to know what are the maximum compressive and tensile stresses. All right. So now let's recall that from C, or in other words, from the neutral plane all the way to the top is our top portion, 0.02734. That will be a C value. And another C value is from the center all the way to the bottom toward the minus y direction, minus y axis, give us minus 0.02266. That is another C value. So let's plug in the first C value of 0.02734. The moment we found it to be 1,200 Newton times meter, the C is this one divided the the area moment of inertia for the whole cross section So the answer in here will be negative 8.174 times 10 to the power 7 Newton over meter squared, or Pascal. This, because it's negative, on the top we will have compressive stresses. Same thing we will do for the bottom, but we will use the other C value, which will be the negative 0.02266. And don't forget the negative in front of the expression. And here it will give us a value of 6.774 times 10 to the power 7 Newton over meter squared, or Pascal. And since we have a positive value, it tells us that at the bottom of the beam we will have tensile stresses. Thank you very much. Have a good day.